Alright everyone, so this is going to be chapter 2.2, the infinite square well out of Griffith's quantum mechanics. And sometimes if you see me write like this, infinite square well, that's just kind of my shorthand because sometimes we get lazy. Okay, so the infinite square well is a particular type of environment that we're interested in quantum mechanics. And let's just talk about what it is first. And before we even do that, if you remember, in 2.1, we used separation of variables to solve the Schrodinger's equation. And what we found is that the time-independent Schrodinger equation, which is what I have down right here, we couldn't really go any further with that like we could with the time dependence part, the rho of t. And that's because it depends on this potential, V. So what we're doing here and in the next couple sections is we're going to be looking at different types of potentials and solving our time-independent Schrodinger equation with that potential. So for an infinite square well, the potential is 0 if x is between 0 and some spot A, and it's infinity if it's anywhere else. Infinity else. And this picture here, figure 2.1, kind of depicts what we're looking at. The 0 to A was a little bit arbitrary. You could imagine this box being shifted in different spots from maybe A minus 2 to A over 2 or what have you. But fundamentally, it's the same type of problem. Now, before we actually get into solving it, you might say, well, that's not very realistic. You're never going to have any sort of source of infinite potential. And why that's technically true, it's still an important environment worth studying because, number one, you can often do approximations with an infinite square well. So you can look at maybe n behavior and see what you get. And then number two is it kind of it gives us a rather easy example to work through. You could have a much more complicated system, but we don't really want to jump into that. We want to start with something maybe a little bit simpler before we get into more complicated stuff. Okay, so with that out of the way, I said we needed to solve the Schrodinger's equation, and we're going to do that. So in this potential, you can almost think of it as being 3 spots. One here, one here, one here. 3 regions, maybe a little bit better. Now region 1 and region 3, we really don't have to do much to solve for psi. Psi of x is just 0. There's no chance you're going to find a particle at this potential where the potential is infinity. So outside of the well, we already know that psi is going to be 0. So the only spot we really need to worry about is that second region in between, where our potential is 0. So if we look at the time-independent Schrodinger equation and we just plug in v equals 0, we get minus h bar squared over 2m. The second derivative of psi with respect to x equals e times psi. Okay? You can also solve for the second derivative of psi with respect to x squared, and that's minus 2m e over h bar squared times psi. Okay? Now, if we define a variable k, and we say k is equal to the square root of 2me over h bar, then k squared is 2me over h bar squared, which looks pretty similar to this, only there's a negative sign, so we can say the second derivative of psi with respect to x is minus k squared psi. Now, one thing I want to mention that is a little bit subtle but worth noting is E. Now, if E is negative, then we would have imaginary values for K. But we actually don't need to worry about that because in a previous problem that we did, what was it, 2.2 I think it was? I think it was 2.2. We know E has to be positive. So if you're wondering about that, you can look at the previous problem and hopefully that'll help. Okay, so yeah, it was problem 2.2. So E has to be greater than 0 or equal to. Okay, so now this is a differential equation that is pretty common to solve. This is just like a spring problem or any sort of simple harmonic motion. And what we know is that psi of x is equal to, we'll call some constant A, sine of kx plus b cosine of kx. So this is a pretty simple differential equation. Hopefully you're okay with that. You could take two derivatives if you'd like, and what you would find is that this is a solution to that differential equation. But we can do a little bit better because there's boundary conditions we can consider. Okay? So what are our boundary conditions? Well, there's a couple. The first one, we could say psi at 0, our wave function has to be continuous. So at 0, to the left of 0, we know psi is 0. So to the right of 0, it also has to be 0. So this is basically what we did, was say psi to the left equals psi to the right. And that is true also for psi at A. So psi at A needs to also be 0. Because to the right of it, it is 0, and our wave function has to be continuous. So let's start with psi of 0 equals 0 equals, well, sine of 0 is 0, plus cosine of 0 is just 1, so plus b. So from this first boundary condition, we can see that b equals 0. In other words, we don't even have this cosine term. Okay? So we have that. So we can really write psi of x as a sine of kx. Great. Now once again, we want psi of A to equal 0, which means A times sine of k times A. So we can kind of use the zero product property here. If this term is equal to 0, either A equals 0 or sine of ka equals 0. The problem with A being 0 is if we let A be 0, we just get the 0 vector, psi of 0, or psi is equal to 0, which is our trivial solution that's non-normalizable, so we're not actually worried about that. So instead, we know that sine of ka, those are the solutions that we're interested in. Okay? Well, for that to be true, the argument inside sine, ka, has to be 0 plus or minus pi plus or minus 2 pi plus or minus 3 pi, and so on. But we can actually simplify this a little bit. So first off, if we do k equals 0, well, again, that's essentially telling us that psi of x equals 0. Okay? So we don't actually need this term. That's, again, the trivial wave function. Okay? Now, as for the other terms, we have the positive and the negative terms. But remember, sine is an odd function. So sine of negative x is the same thing as a negative sine of x. So this negative sign that you get from the negative arguments, well, that can just be absorbed inside our constant, since -1 is a constant. So really then, what we have is Kn equals n pi over a. So we take our positive pi's, we divide by this a, and we have n of them. So n is an element of the natural numbers, which, if you're not familiar with that set, it's just 1, 2, so on. Okay? Well, remember up above how we defined k, the square root of 2me over h bar. Is this h bar squared or h bar? I think just h bar. Double check ourselves. Yeah. Okay, well, k is equal to n pi over a. So now let's square these two sides, and you get 2me over h bar squared equals n squared pi squared over a squared. Or, if you want to solve for e, you get n squared pi squared h bar squared divided by 2m a squared. Okay? So these are our allowed energies for the infinite square well. So you can't just have a continuous value of energy, you can only have discrete allowed energy values. And that's what this n is giving us. Okay? So we have what k is equal to, we have our energy. So all of this is important. There is another thing we need to do though, and that's find out what our capital A is. Because remember, we know that it's not 0, but we also need to normalize our wave function. So if we integrate from 0 to a, because everywhere else the wave function is 0, and we integrate our probability density, we know that that has to equal to 1. That's just our normalization condition that we've talked about before. So what we need to do is solve this integral. Okay. So let's see. If you remember your trig identities, sine squared of x is equal to 1 minus cosine of 2x over 2. That's a trigonometric identity that we have. So we can substitute this in then, and we get the square of our coefficient here times the integral from 0 to a is 1 minus cosine of 2kx, all of this over 2, dx equals 1. Okay, so I'm going to factor out the 2, and we will integrate from 0 to a of just 1 dx minus the integral from 0 to a cosine 2kx dx. And again, this is all equal to 1. Alright, so this first integral is easy. That's just a. And then minus, let's see, if we integrate this, we'll have 1 over 2k sine of 2k x, and we're going to evaluate this from 0 to a. Okay? So let's see. We have And then obviously if we plug in 0, that's going to be 0, so we don't have to worry about that. Now this is going to be just sine of 2k, but remember what k is. K is n pi over a. So sine of 2 n pi, the a's cancel. This is 0 because of the fact that sine is the periodicity of it. So then this is really just a times this a squared over 2 equals 1. So then our normalization constant is just the square root of 2 over a. Awesome. So now we can write our wave function as a normalization constant times just sine of k x. Okay? So I think I'm going to start breaking these up a little bit, the videos, so they're not super long, because there's also examples I want to get through. That was my dog that just yawned. So I think this is a decent place to stop. We were able to get the wave function and the energy equation, and we kind of derived everything. What we're going to do in the next video is we're going to talk a little bit about this wave function and some of its properties. So until then, maybe you can think about what some of these properties might be. And we're going to go through some proofs and hopefully some examples. So hopefully this helps you get started, and if you enjoy this sort of thing, please like and subscribe. I'll continue this series, and it also helps me grow, which is what I'm trying to do. So thank you guys.